Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aryavarth College, University of Delhi. So in this lecture series, which is titled as Operating System Concepts, in the previous lectures we have completed with the topic of process synchronization, and we have seen classical problems of synchronization and solutions towards those. Now going further, today's topic here is about CPU synchronization. Now we will try to understand what is this CPU synchronization and what are the kind of terminologies which are covered inside this particular topic. So first of all, let us try to understand one more we can say venture of scheduling, that is CPU scheduling. Now let us consider a single processor system only in which only one process can run at a time. Now what will happen? One process is running at a time, and when that process is not running, that means when another process is being loaded, the CPU is free and it is sitting idle. So other processes are waiting until the CPU is free. And now this was about a single processor system in which we can say that only one process is running at a time. Now in order to combat this particular situation, we in the earlier classes we have seen the idea of multi-programming, which is like having some multiple processes running at all the times. Now why this was necessary? This was necessary in order to maximize CPU utilization. Now in a multi-programmed operating system, what is happening? One process, let's say, is kind of taking up some input output device, other is taking the CPU, and then so on and so forth. So this is the idea in order to have the optimum utilization of CPU. And this CPU scheduling, we can say it is a basis of this multi-programmed operating system. So what will happen in this scheduling thing? This is actually kind of removal of a process from the CPU and selecting another process based on a specific strategy. Now what could be that particular strategy? That we will kind of debate later on. But let's say one process is one process has been assigned with CPU for some time, and maybe later on you are going to take the CPU from that particular process, and you will be assigning it to another process, and it is kind of that the another process or the next process which I am talking about is already available in the main memory, while in the single processor unitasking system, if we talk about, that process is not available there and it has to be loaded specifically. So basically your process scheduling or this type of scheduling is an integral part of multi-programming applications, and your operating system allows more than one process to be loaded into usable memory at a time, and then the loaded shared CPU process uses repetition time. So this is what is happening in a multi-programmed system. There are multiple processes in the memory, and we will be taking one process from that. CPU will be allotted to it for the time it is kind of required, or maybe based upon some strategy, and then when that particular process is not given CPU anymore, the next process which is already available in the memory will be taking the control of the CPU, and this whole scheduling is done by operating system. So basically we can say a process will be in the waiting state, and now while I am quoting the waiting state, this is the exact terminology what we have gone through in the lecture of process scheduling. So a process is in waiting state until it is executed, and why it is in a waiting state? It is basically waiting for the completion of some input output request. Now in a non multi-programmed system, the CPU is going to sit idle, and all this waiting time is in a way wasted because no useful work is being done here. because your CPU is sitting idle doing nothing. But when we are using multi-programming, we can use this idle time productively, because there are several processes which are kept in memory at a particular point of time. So if one is not using the CPU, others are always ready to use the CPU. Now when we talk about that the several processes are kept in memory at a particular point of time, what process memory I am talking about? So basically here it is very inevitable, or it is very necessary to have an idea of the process memory. This process memory, which is memory area for the storage of processes or for the storage of various data of processes, this particular section is divided, this particular part of the memory is divided into 4 sections. What are these sections? One is the text category, another one is the data class, third one is the heap, and the fourth one is the stack. So in text category, the code, the program code which is there, which is to be read from the fixed storage when the program is launched. So any program which is stored in a particular file, maybe it's .c or .py, whatever, that particular program code is loaded into this text category. Apart from this, we have the next section which is named as the data class. So the data class is or the data section is storing all the variables which are global variable and static variables. Then we have the section for heap memory, which is a flexible section, I can say, and it is used for dynamic memory allocation. So which dynamic memory allocation I am talking about? Let me take here the example of C and C++. If we are going to allocate memory using the functions like malloc or calloc, or in case of C++, if it is new or free and then delete is there. So that kind of dynamic memory allocation I am talking about. All that dynamic memory allocation happens in the section of the heap. That means from that heap section, that dynamic memory is allocated to the variables, we can say. The last section is used, the last section is named as stack, which is used for local variables. So here we have the text section for the program code, then the data section in which all the global and static variables are used, local or stored, then we have local variables which are stored inside the stack section, and then we have one flexible and the section which is used for dynamic memory allocation, that is the heap section. So we have 4 we can say sections of the process memory, and all these 4 sections are shown here in the figure. So the figure says we have some high addresses and some low addresses. Inside the high addresses, we have space for command line arguments and environment variables. Environment variables are very common topic in many of the programming languages like Java. Then in high address, we have a stack section which is growing downwards, if you can see here with the help of an arrow. Then within this section we have also heap, and this heap section is growing upward, and we also have a low address area in which the text is there. So this text, stack, heap and the data section is all about this process memory. So here if you can see, you can find all those 4 sections inside the process memory. So this is a figure which is explaining what I have told you about the 4 sections. Now next, a topic or a kind of, we can say, terminology which is very important when we talk about CPU scheduling is CPU and input output burst cycle. So when we say that there is a process which is dependent on CPU more as compared to input output, that means the execution is more as compared to the input output according to what process is comprising of. So that particular process which is having more CPU requirement as compared to the requirements of input output are known as CPU burst processes, we can say, On the other hand, if we have input output requirement of input output more as compared to CPU, then that is known as input output burst. So your input output burst cycle is actually dependent on the process, or actually comprises of, we can say, the process execution, which is consisting of a cycle of CPU execution and input output wait. So there is a process which is going to alternate, or which is, we can say, is going to switch between these two states. One is the state of CPU execution and another one is the state of input output wait. For a typical process, the execution begins with a CPU burst, that means a requirement of CPU and CPU is being given. Then it is followed by an input output burst, then it may followed by another CPU burst and then another input output burst, and so on and so forth. And finally, as it started with the CPU, the process is going to end with the CPU burst, or the final CPU burst ends with a system request to terminate the execution. Within that CPU, within the final CPU burst, there will be a system request to terminate the execution. So basically, a process is entering into the system, starting its execution with a CPU burst followed by an input output burst, then CPU, then input output, depending on the requirement, how many times it needs it. And finally, there will be a final CPU burst which is going to end with a system request to terminate the execution. Now, when we talk about CPU scheduling thing, what we need to do with this CPU input output burst cycle is, this duration of CPU burst we need to measure in order to, we can say, in order to gauge the utilization of CPU, that how much CPU is going to be required, or in order to have the maximum CPU utilization, these CPU burst has to be measured extensively. But the one fact which is underlying here is, this CPU burst vary greatly from a process to process, and we cannot generalize it. But it varies greatly from process, not only from process to process, but it also varies from a computer to computer. And if we after this measuring or after studying, if we are going to plot a frequency curve, we are going to have a frequency curve which is generally kind of an exponential or hyper exponential in its shape, as it is shown on the screen. So generally, if you can see, the frequency of the CPU burst is, we can say, large, then followed by some smaller CPU burst durations which are plotted on the x-axis, and on the y-axis the frequency has been plotted. So this curve is generally characterized as the exponential, or we can say hyper exponential, with a large number of short CPU burst and a small number of long CPU burst. So short CPU burst, that means the time when your process is looking for CPU, or when your process is requiring CPU, and this is large in number, that means many a times this is going to happen, and these are short CPU bursts, short in terms of duration, while there is also a requirement of long CPU burst, which is small in number. So if we plot that particular measurement, we are going to have a curve which is exponential or a hyper exponential curve, as it is shown on the screen. So this was about the CPU burst or input output burst. While this concept we will be using further in the detailed study of the CPU scheduling. So basically, if a process or if a program, we can say it is an input output bound program, that means it is more dependent on input output activity rather than CPU. So an input output bound program is having many short CPU burst, while if I am talking about a program, or if I am talking about a process which is a CPU bound process, then it might have a few long CPU bursts as well as. And this distribution, why we have studied this CPU input output burst cycle here, because this distribution can be important in the selection of a CPU scheduling algorithm. So as I have told you that when to assign and when to take the control of a CPU, take the control of CPU from a particular process will be decided on the basis of some strategy. So those strategies we in the technical terminology we call those strategies as CPU scheduling algorithm, and this CPU input output burst is going to be a very important parameter, we can say, or as an important point in the selection of the appropriate CPU scheduling algorithm. Now if we talk about the process scheduling, so here we have three types of process scheduler. If you remember, we have gone through these schedulers already when we talked about the process thing. So these are long term scheduler, which is also known as the job scheduler. Then we have short term scheduler, which is also known as the CPU scheduler, and in between we have a medium term scheduler as well. So as our today's topic is CPU scheduling, we will be focusing on the CPU scheduler thing. So whenever now in a typical system, in a typical multi-programmed system, what is happening, whenever the CPU is becoming idle, what is the next job of the operating system here? The next job of the operating system here is to select one of the processes which are available in the ready queue. Now please recall, ready queue is the queue of the processes which are ready to take the control of CPU, or which are in a way we can say waiting for the CPU to be assigned to them. So that queue is the ready queue. So whenever the CPU is becoming idle, the operating system must select one of the processes in the ready queue to be executed, and this selection process is carried out by the CPU scheduler, or we can say the short term scheduler. So that means this short term scheduler or CPU scheduler is the component of the operating system which is going to select the process from the ready queue. That means whose state we can say will be changed from waiting to, we can say, from ready to running. So the scheduler selects a process from the process from the available processes in the memory that are ready to be executed, and allocates the CPU to that particular process. And when all the processes in the ready queue are lined up waiting for a chance to run the CPU, so that means whatever processes are available in the ready queue, all these processes are waiting for the CPU to be given to them. And when we talk about these processes are waiting up in the line, so how these processes are represented inside this queue, we can say. So here is we can say the records in the queues are generally process control blocks of the process. So let's say a process P1 is waiting in the ready queue. So ready queue or any other queue, let's say. So what that ready queue is going to be, kind of, we can say, consist of for that corresponding to that particular process, that is the process control block. So process control block of one particular process, then process control block of the another, then process control block of the third, and then so on and so forth. They form a queue. So now the task of the short term scheduler is to schedule the CPU for the number of processes present in the job pool. So we have a job pool and all the processes are looking for the CPU. The short term scheduler is going to schedule the CPU for these processes which are available in the job pool. Now this process is actually not that simple as it seems to be. It involves kind of more technicalities, we can say. So whenever there is a running process as in the process is already having CPU and the process is running, it is requesting some input output operation, then what will happen? Now as the process has requested an input output operation, it has to be taken out from the CPU. That means CPU will no longer be allocated to that particular process, and then its state will be changed. So, whenever a running process is going to request some input output operation, then the short term scheduler saves the current context of the process, or we can say is going to save the process control block of that particular process. Now, why it is being saved? It is being saved so that it can be used when later on the process wants to resume with the kind of execution, and it is allocated the CPU again. So, after saving the process control block, or after saving, we can say, current context of the process, the state of the process is changed from running to waiting. So, running state is actually which is having CPU, which is having the control of the CPU, and during this time the process will be in the waiting step. Meanwhile, now one process has been taken from the CPU, that means now your CPU is in a way we can say is sitting idle, and it is ready for the next process. So, it is the short term scheduler who is going to pick another process from the ready queue. Ready queue is the queue of all those processes which are ready to take the control of CPU, or we can say the processes which are looking for the CPU. So, one particular process is picked up. Now, which process is going to be picked up, that depends on the strategy, or that depends on the policy. That is a policy decision we will be studying later on. So, the scheduler is going to pick up the another process from the ready queue, and the CPU will be assigned to this particular process. Now, what is happening here? The happening which is going to occur here is one process from running is going to change its status to waiting, and some process control block or context is being saved, and CPU has been given another process from the processes available in the ready queue. So, a context is being changed, we can say at the CPU level. If we can say the context has been changed, earlier it was some one process and now it is the another process, and this whole we can say process of taking the control of CPU from one process, saving its states, saving its context, changing its state, and assigning the CPU to another process. This whole we can say this whole game is known as the context switching. So, apart from this context switching, or apart from whatever this CPU input output burst cycle, we have some more terminologies which we will be using when going into details of this CPU scheduling. Let us crawl through those terminologies once. So, the first term is about burst time or execution time. So, burst time or execution time, we can say it is the time required by the process to complete the execution, and this is also known as the running time. The second terminology is arrival time. It is very simple, as the name indicates. It is the process, it is the time when the process enters in a ready state. Then we have finish time, when the process, the time stamp, or we can say the time when the process completes and exit from a system, that is its finish time. Then we have CPU input output burst cycle. This is we have already gone through. This characterizes the process execution which alternates between CPU and input output activity. CPU times for any process, because of the speed of the CPU, are usually shorter than the time of input output. Input output devices are, we can say, are slower as compared to the CPU. Apart from that, we have two more terms. One is the turnaround time, which is the time difference between completion time and arrival time. So, completion time minus arrival time is my turnaround time, and another thing is waiting time. So, waiting time is the time difference between the turnaround time and the burst time. So, all these terms which are finish time, CPU input output burst cycle, burst time or execution time, arrival time, turnaround time and waiting time, all these terminologies we will be using in our upcoming lectures of this topic CPU scheduling. So let me recap this whole lecture here. So initially we have understood what is this CPU scheduling, then we have gone through CPU input output burst cycle, and after that CPU input output burst cycle we have seen some terminologies, and we have also seen the concept of CPU scheduler and context switching. And here we have a list of references which is being used for the preparation of this lecture. I hope you have enjoyed the lecture. Thank you.